Well, can you believe it, everybody? Can you believe it? We actually are here having a great time. Just got started. And it is I, Marc D'Antonio, with SkyTour livestream for this wonderful date, which is not correct. I have to set the date correctly. That's great. All right, and we'll do that in a second. All right, my mistake. And I also want to welcome Daryl to the stream. Hey, Daryl, how are you?
Hello, Mark. I'm good. Can you hear me okay?
Yeah, everything's fine. As we said before, you're doing just fine.
Oh, yeah,
Daryl
then,
has a new mic, and he's a little uncertain of it, but it's really good.
yeah.
It sits farther from you. That's why it makes you feel uncertain. There goes a satellite right there.
Well,
Zing.
no, you must have muted me before we went live. I couldn't get your attention, I guess.
Oh, yeah, maybe I did. I muted you from here so that you wouldn't hear keystrokes and stuff like that. The pitter-patter of little fingers.
Very good.
That's okay. All right, let's see here. Let me, first of all, fix the date. I realized that I messed that up. Let's just get that taken care of right now. And we want... Oh, that's here. Okay, just a sec. It's nice to be with everybody. I'm giving some time to folks who are coming in because it's been a while. Yeah, let's find out what's going on. All right. There we go. And then the date should pop in. There it is. We are all set. Okay. So I want to welcome everybody. It's good to see you. Nicey nice. I'm looking to see where everybody is. We've got a bunch of people in here already. Nice to see Tim F. Hey, Tim, you're back as the first one. And then Cyclone's with us. Terry Haig. Mazif. Hi, Mazif. How are you doing? And we have Renee Cruz. What's happening, Renee? And you guys are the first ones, and there'll be more coming in as we go. Tonight, we have a supernova that has occurred. This is not it. This is actually Alpha Leo, the brightest star in Leo, known as Regulus.
Fabulous.
Yep. And we will be using this. I use this star as a focusing point, and I'm going to actually take care of doing some of that right now. Here we go. Haven't done that yet, and I would like to. So we're going to do a scan inward in our very visual, wonderful focusing process. Temperature out there is 28.6 Celsius. As you know, that's pretty warm. Hello, Izabela.
Who's here?
Yeah. Oh, Renee says on April 14th there in San Francisco, they saw an extraterrestrial alien UFO on Market Street between 4th and Kearney, 60 to 80 feet in the air. Interesting. I'd be very interested to hear more about that. You know? Stephen A., how are you? Good to see you. I wanted to mention, too, that I just talked to, not about 45 minutes ago, I got a chance to talk to David Levy, who is the world's premier comet finder. you may have heard of shoemaker Levy. He was one of the co-discoverers of that comet. And he was actually down southeast of Tucson, where Marianne is right now. And Marianne got to meet him, and it was so funny because she's scouting observatory locations for us for our next telescope. We have a guaranteed spot right now west of this spot, okay? And we are going to be possibly making our way to that spot with our third telescope. But the one that I have behind me, which you can't see, is possibly going to be moved out to Arizona. So we'll have 3 out in Arizona. And that would leave us open to put a 4th one out here. We're not taking prisoners, guys. We're actually going to keep adding to our assemblage of telescopes to bring you the best. I want to bring you the best in all this. Okay, so I am I'm done with the focus here, and so we have a beautiful shot here of Leo. I'm gonna ramp us up to 1 second and just do that. Yeah, I'm checking our delays. We had very fast service out there tonight, but it comes and goes. Right now it goes. So we're going to check out Measure 101, where this amazing supernova has occurred in just a little bit here. There we go. There's a 1 second shot. Yeah, we can actually start thinking about going there now, I think. Because that's really pretty. Okay, let's go into our planetarium view and do a search for Measure 101. It's going to be right near the top. Oh, that's right. I did it on my other copy. I didn't do it here. And we'll go there, and you'll see that shift around. It's very high in the sky, as you can see. It's literally that's the zenith. No, it's not. That's actually the zenith is. I'll show you where the zenith is. Zenith is over here, so it's very close. If we knock out our Earth coordinates, you can see this is like the dome over your head, and it's literally sitting right up, literally almost at 60 degrees above the horizon. All right. And we'll turn that off, put the coordinate system back on. Hey, Rascally, how's it going? So Betelgeuse is changing brightness again, and that's sparking some renewed interest in this potential that Betelgeuse is going to explode. I think that's pretty cool. All right, so let's now make our way here.
Picked a fine time to start doing it. It's going away now.
Yeah, I know. Which is kind of terrible.
Hopefully, if it goes supernova, it doesn't do it while it's on the far side of the sun from us.
I know.
Orion is dropping off into the sunset, folks.
Yeah, it is.
And it will then start appearing in the morning sky in the weeks or the month ahead. At first, very early in the morning, and then later in the year, it'll be climbing higher and higher, and it'll be high in the sky, maybe still on the late side, midnight, October, I think.
All Alright, let's see what we got here. We're 1 second in. Let's make sure we've got it. Oh, it's still too bright out there. Look at that. It's still too bright. I'm waiting for the sun to set and it's just too bright. Yeah, it's not visible yet.
I tried to warn him, but he wouldn't listen to me.
Oh no, I knew. I was just trying to get an early start. Yeah. I think that the other thing that's happening is it's possible that let me just bring this up here. I think it's possible too that our coordinate systems are still off, which I don't doubt is a possibility. Let me see if I can actually from here, it might be a little too bright to try to plate solve yet, but I'm going to try that. I'm going to try and solve for our position here. So let's do that. First things first. Let's get this down to 1 second again. And crank that up. And that may or may not be enough. I don't know if that'll be enough, but we'll try it. Plate solve uses the pattern of the stars and it actually aligns them. Yeah, we don't have enough stars. So I can try increasing the gain. And that may work. Or I choose a different location to plate solve from. And that's probably a better idea. Where I have some bright stars to choose from. Alright, so we're going to try this now. Needs to be dark. Alright, this looks like a promising field. So let's try plate solving this one. It needs a dark sky to do it. Oh, great. Well, that ain't gonna work. "12 sources." Alright, says it found it. Let's see how that looks. So now what we'll do is we will come in and take that data and put that into our system. And I'm going to do another plate solve right now so that other mess wasn't in there at the same time. And let's see if we get the same results. Flicky flicky.
Yeah.
Alright. Okay, we'll copy that and we'll put that in. Okay. It's consistent, so that means now we can put this in. Alright. This is 14 hours, 29 minutes. "13 seconds of arc. And then waiting. Here we are. And this is going to be plus 45, 1905. 45, 1905. Yeah, it says it's off. So we're going to sync that. And it got it. Okay. So now we're going to go back to our planetarium program and then head back to M101. There we go. And now we'll see M101. There it is. Right there. All right. And now what we'll do is we're going to center it up. And once we center it up, we will be able to went a little too fast and too far. Let's go back the same way. There it is, dead center. Okay, good. We'll set this to that guy. Head off, get a guide star, and let's look for a supernova, guys. This is definitely a cool galaxy. It's a face-on galaxy, and it has a tremendous, those are all Starlinks going by, has a tremendous supernova that's going off in there right now. It's actually not very bright yet, but we're going to try and check it out as best we can. Hey, Cosmic Ray, how are you? All right, so what we're going to do... And by the way, that view right there, that's another view of the camera, of the rather the telescope. So now we have 3 cameras in there. And that actually, just to give you an idea what that view is, let me just put it up big for you. So there's the view. This is looking out through the open roof of the telescope building, okay? The telescope is currently pointing up in the sky. So there you go. That's kind of a neat thing. And now we're there. Okay, so let's do a 25-second photo of this. And let's drop out of our night vision mode, go into a live stack mode, and clear this. There we go. And we'll see it right here in just a sec. Hey there, Michael Hedrick. Hey, Gladys1, how are you? Actually, Gladys, we're about to look at the supernova right now. All right. And if it's bright enough, we'll see it. Okay, it looks reddish right now with this haze because it's not quite dark out there. I'm kind of pushing it a little bit.
Golly, I think I can see it already. Looks like it's brightened since last night.
Right here?
Farther out.
Oh, there it is. Holy cow.
Yeah, right there.
Yeah, holy cow. Wow. Yeah, it's there. That's nice. All right, let's...
Quite a bit brighter than the pictures we saw last night.
Way brighter. Let's color correct this and drop some of the red down. We don't need that. As it gets darker, we'll be able to see this better. Okay. Now look at that bright spot right there, and it's remarkably blue, Daryl, which is what we'd expect for a supernova.
Mm.
Very cool. All right, let's zoom in on. That's beautiful.
Hopefully.
Oh, look at that. That's it.
That's it. That
That's
has
a very
increased in brightness a ton since last night.
Yeah, I think we're hitting it. It was very dim last night, but we didn't actually image it last night.
Yeah.
Yeah. So, for those who just want to see what we're talking about, it's that little white spot inside that square. Okay, and I'm sorry that it's not dark enough yet, so the colors aren't rendering perfectly yet. So, it'll be fine in just a minute. I'm gonna. Alright, so let me get out of this and bring us over to the left of our curve here to give us more detail in here. Alright, there's our galaxy. And let's see if we can color correct yet. Well, we got a lot more data. Okay.
Mark, we looked at the supernova in an NGC object last year.
Hey, we did.
NGC 4647, I think it was, or something like that.
Yeah, something like that.
It was near M60 in Virgo, I believe.
Yeah. This red color is just temporary, guys, until the sun fully sets. The camera is very sensitive to the red sunset light, so we're seeing it here in our images, and you can almost not correct it away. Go ahead, Daryl. I'm sorry.
When we watched it last year, we saw it on quite a few different nights, and
we saw it change.
We could track the change over time, and here
we're gonna do the same here.
It was just discovered yesterday, and we managed to catch it tonight already, and it has brightened considerably since it was discovered. So we may be in for a show in the coming days and weeks with this thing.
Yeah. And as it gets darker out there, we don't even have the end of astronomical twilight yet. So if we were to take a picture, we would still see sunset. Okay. And that's just something that unfortunately we just have to wait for. And I'm pushing it, guys. I mean, it's 11:30 and not quite dark out in Arizona. I'm in Connecticut. It's 11:30 for me, but it's only 8:30 out there. Okay, let's
I think
try.
Astro Twilight is 9:08 Arizona time tonight.
Okay, yep. Hey, C&D boy, how are you? Oh, Gladys, it's gonna get better. As the sun sets, the red color here is going to go away, and we're going to see the true colors of Messier 101. But look at that beautiful supernova. Isn't that something? That's really pretty. Okay.
Oh, that is so much brighter than it was last night even.
It is really bright.
And folks, what they often say when we see supernovas in other galaxies, as Ray was alluding to earlier, a good supernova can be as bright as the entire rest of the galaxy it's seen in. It is so tremendously bright.
I can show people a simulation of that. First of all, this is what we got. Okay, this is Messier 101 with the supernova right there. And we're still stacking here. But let's see if we color correct, if we're going to get a better color here. Yeah, it's starting to. Some of the galaxies red will be the last to go. You can see that the sky is getting darker now. And this is cool. Let's clear this and get another shot. Okay, stack has been cleared. When I say stack, to those who don't know, that's right here. This is the stacking area here. And this is our data area. And so what we do is we take an image, take another image, align it with the first, and put it on top, and just make an image sandwich. And what that does is it takes all the small sensitive data and it brings it forward and makes it the most prominent thing in an image. And we don't have a prominent image yet because we're waiting for the sunset. You can see now the blue spiral arms are starting to come out a little bit. And once we get close, we'll be able to correct out the red. As you can see, I'm already to the point where I can correct out a lot of the red. And let's bring this curve in here to kind of brighten it up a little bit. And there's your supernova right there. That's really pretty.
It is.
And again, to those who may not see it, we're talking about this object right there. That white dot you see right there, that's your supernova. And as you know, I recently added the ability to draw over our live stream so you can see exactly what we're talking about. I can also, as I've often done, I can also come up and I can also come up and say, well, here it is right here. See, there's the supernova right there. Right there, that guy, right there. That guy's the supernova. I mean, that's pretty cool. And here I am, I can say, hey, look, I've got the supernova in my hands right here. Just grab it right there. I got the supernova. Pretty cool. Oh, and there you can see the other image. Screen real estate is at a premium. But we're doing okay. This is doing better. Let's see how the sky looks now when I correct. Okay. It's getting better. Yeah, see, it's getting better. Still got to correct out some of the red. But you can see that it looks great. This supernova here, stellar evolution, as I'm an astronomer, that's what I went to school for, so I tend to discuss these things in terms of the actual science we know. And that's what SkyTour live stream is all about. So when we're looking at a supernova like this, what we're seeing, right, what we're actually seeing is a star that has run out of fuel to create fusion reactions in its core. And stars will make, they start out with hydrogen, and stars make helium from hydrogen. Then when the helium starts to fuse, then the helium makes carbon and some oxygen and some nitrogen. And you can see this is our periodic table being built by stars, and that's just what's happening. And so I think that one thing to keep in mind is that when stars run out of all the potential fusion fuel, then there's nothing left, and a star is always pushing out at the same rate that it's trying to collapse from its own gravity. And that outward force and that inward force are balanced. Now, the term for that is hydrostatic equilibrium. And hydrostatic equilibrium is very important. Our star has hydrostatic equilibrium right now, and so it's able to hold itself up because it's pushing outward with a vast amount of radiation. And then that star Our star is also fighting being collapsed by its own gravity. All right, and so that's something that is also important. And so that equilibrium is what makes a star stay stable. Okay, and in the case of a star that's run out of nuclear fuel, the core stops outputting any radiation. And when that happens, the entire weight of the star starts to go crush inward. And when that happens, two things happen to herald a supernova explosion. First, we'll see a massive, massive rush of particles we call neutrinos. And this neutrino flux, or this neutrino energy coming from a star that's about to go supernova, is something. We have a little wind, by the way, so you can see a little blur. When a star is going supernova, the first thing that leaves the star are neutrinos. Neutrinos are not as encumbered by the rest of the particles and plasma in a star, so some of them get out. Literally, 1 out of a billion actually get out. And that's still enough so that millions and billions of neutrinos will reach us from a star that's going supernova. Now what happens is that neutrino flood gets out of the star and heads on out. And that'll reach us in however much time it takes. And then over a few hours, then that shock wave of that exploding star is moving outward inside the star. When it finally reaches that surface of the star and bursts out, that's when you actually see a physical, visible change in the star, and it actually is in the process of blowing up. It's a slow process in that way, but it's an instantaneous process. Once it reaches the surface of the star, that now the star becomes totally disrupted, as we call it, and that disruption to the star is the supernova. It's so hot that it's a hot blue light. And as you notice in this image, that's hot and blue, isn't it? Are you back with us, Daryl? I heard you going away there for a bit. He's not back yet. Okay, so that said, if you notice, I'm going to try and correct and see what we get for color here. Yeah, we're getting better now. As the sun goes down, the colors of the galaxy are more natural. See, that's getting far better. All right. Okay. So one thing that will happen from time to time, this is really looking pretty. Yeah. Really pretty. Very impressive, very impressive. Okay, so when you can see these lines, this red one here, this green, blue, green. What's going on is the guider is trying very hard to keep up. But there's some wind bouncing the tube around, so it's doing an admirable job considering that it's undergoing this wind here. But I'm going to keep correcting. All right, and there is our supernova right here, and I'll just put this little box around it. It's that blue thing right in there. That's it. That's ongoing right now in Mesher 101. Okay. So, and Papa Tom is here. Yes, Papa Tom says it's getting very bright now. Yes, it is. Look at that. Look how bright that is in there. Isn't that incredible? And yesterday when I was looking at shots taken in another observatory, I noticed that this supernova was actually much, much dimmer than this little area right next to it. You could barely see it. Now it's brightened up incredibly. incredibly. It's brightened up incredibly. Okay. Daryl has lost his connection, so we're going to get him back here. So here we go. Are you back with us, Daryl?
I hope so.
Yeah, you are. Okay, good.
I lost my internet connection.
Are you having storms?
Not right now. Not that I know of.
Okay.
Can you share a screen with me again, please?
Maybe. Yeah. Here you go. So, what I want to do to make this a good image, I'm going to clear this, and we're going to start again. And now that it's darker, we should start to get a more realistic looking view right from the very start. It's 82 out there right now. Let's first do this and do this. There we go. Notice how noisy this looks. Okay, this is what happens with our first image. Remember the stack? The image sandwich gets rid of a lot of that noise because all these little colorful dots, that's random noise. Watch this now. Here's the second one. Okay, when the second one comes in, look at that. What a change already. So that already starts to randomize the noise that's out in the deep space locations. Now you might say, well, what if there's something dim out there? Well, that dim thing is a data thing. It's going to come back over and over and over for every shot. So it's going to get brighter and brighter and brighter as we stack more and more and more. So more stacks are always better. And that's what we're doing here. Wow, this is something. I'm liking this.
You can see the blue in it now, too.
Yeah, that's what I was trying to get at with this because I wanted to make sure we could see that. That blue, as I said, that blue is a very, very, that's a hot, expanding supernova right in there. And boy, let me tell you, that's not something to be trifled with. We're talking about, hundreds of thousands of degrees in that expanding cloud. And that's down from millions of degrees. Now, close to the star, it's still going to be millions of degrees as it's expanding out. But as it gets thinner and thinner and thinner, the temperature will get lower and lower as well as it loses some energy. Really cool. Hey, Lewis, how are you? Yes, Lewis, this inside that red square is the star in Mesher 101 here that exploded. It's a beautiful supernova. Yeah. This is one of the best supernovas, I think, so far of the season, don't you think?
Of the season?
Oh, Galaxy season so far for us.
Oh, but it's not like they happen every day.
I know.
Certainly the best one this year. The only one this year.
Yeah. Terry Haig says it was raining here all day. Yeah, Terry's also from Connecticut, and yes, it was raining here too. I couldn't even take Dingo, our Astro dog, out for a walk today because it was too nasty rainy. You know, that's really nice.
Michael Hedrick Wet Shaves has a question for you. I could answer it, but he asked you, so.
It's so bright that it's reflecting on the left. No, Michael, that's actually what you see there. That, in fact, let's zoom in on that because that's a good question. I'd like to answer that in a proper way. You're looking at light. Everything you see here is light that's being emitted by something. Okay, so this is a nebulous region inside here. This is the supernova. Notice it's the bluest thing in the entire image. That's because it's the hottest thing in the image. And just to give you an idea of how bright that is, if we take this down and remove the galaxy almost entirely from the view, like this, look at how this barely changed. See how that barely changed? That's because this is actually a very bright object, and its light is approaching potentially the brightness of the entire galaxy already.
Yes.
Yeah, that is something else.
Notice the
So,
stars are oblong. You got wind out there?
yeah, I had mentioned that a few times already. It's
Yeah.
unfortunate that we have some wind, but that's okay. Nothing's going to stop us from looking at M101. In fact, we're going to take and save images of this.
Yeah, that
101
object to the upper left of the supernova, that's a huge area all by itself. It's
right under the red guiding artifact right here.
yeah,
Or this.
that is what I meant right there.
Oh, okay, yeah.
Yeah, that was much brighter than the supernova just last night, and now the supernova is brighter. That's a big
Yeah.
H2 or a star factory region right there.
Yeah, it is.
That's very
I just
large
added
all by
some.
itself.
I just added some image sharpening to this to enhance some of the detail. Yeah, that's something.
It is.
Well, I hope you're liking this, guys. This is Measure 101.
I am.
And yeah, I know you're liking it. I'm hoping you're liking it. We're all liking it.
We could be seeing the death of an entire solar system, civilization, perhaps.
Well, yeah, let me, I had a conversation with another astronomer the other day about that. And here's a thought I had about that. Stars last on the order of 10 billion years if they're like the sun. If they're M-type stars, the cooler stars that are out there now, none of them have gone and died yet. We haven't seen a single M-class star in the entire lifetime of the universe that has died yet. And that's because every one of them that's in existence has been in existence since it was formed and will go trillions of years. Fusing quietly hydrogen into helium and maybe helium into some carbon. But most of that's going to happen over trillions of years. And the reason is because the stars, only the core in stars like the sun are actually fusing anything. That stuff on the outside that makes up the rest of the sun, well, that's actually just very hot gas. It doesn't play a role in fusion. In fact, it stops a lot of the energy from getting out sometimes. But what happens with a star like an M star, very, very small stars, maybe a little larger than Jupiter, 100 times smaller than the sun, say, is the entire star is what's called convective, like a boiling pot. So stuff down below gets dredged up to the top, and then the other hydrogen gas that makes up most of the star on the outside gets pulled down into the core, where it can be used for fusion. And this actually creates a long-lived star. So that's why they have such long lives, is because they have an ample supply of hydrogen. Really interesting. Let me just color correct, get rid of the red. Yeah, look at that. All right, so but stars like the sun, they only have the core, and the core, if you strip it away after a star like our sun dies, the core that's left is about the size of the Earth, and we call it a white dwarf. Okay, so the core is a little bit bigger than that in a star like the sun, and so this is Supernova 2023 IXF. Is that what you said, Daryl? Okay, very cool. Thank you for that. I think it's probably a good idea to add that. Here we are. So there's Supernova 2023 IXF. And it's just an incredible, putting on quite a show tonight. Really looks nice. Really pretty. And I swear it's getting brighter as we speak, you know. But this is neat.
Say that again.
I swear it's getting brighter as we speak.
I think you may be right.
Yeah, some of this light is coming in. I'm going to save this just like this. Alright. We'll save it. And there we got our 16-bit stack saved. I'm going to save it exactly as seen. And it's going out to the, it says up here, Measure 101 with Supernova. Okay. And now I'm going to clear this. And we're going to start this again. And do a comparison. To see if anything changes. So Gladys says, so it's going to take trillions of years to know what happens after the supernova. No, actually, Gladys, the trillions of years is in relation to stars that are called M-class stars. They're small little percolators. This was certainly not one of those. Okay, this was a massive star that probably only was going to live for anywhere from 10 million years to 100 million years or thereabouts. So it's the big massive stars that do the exploding. Those small little M stars, if you saw my Facebook page, I put something up there that talked about the Helix Nebula. And the Helix Nebula is the kind of nebula that it will occur when a star like our sun dies. All right. And so our sun is not very massive, and our sun is not going to do a supernova thing like this. A supernova thing would just obliterate everything in the solar system, and if humans were still here at that time, well, then too we would find that mostly that there'd be mostly no life left in our solar system from that. Now, one thing to keep in mind about that, however, is that the interesting thing about supernovae is that if there's a civilization, I started to talk about this before, they got sidetracked, sorry. You know, the stars will live, you know, the stars that go supernovae are massive. So if there is a habitable zone around that star, it's going to be pretty far away from the star. Our habitable zone is 1 astronomical unit from our type of star, which is the sun, and that distance is 93 million miles, plus or minus. And that 93 million mile distance is for a star like our sun, which is a G-type star, G. And they go from O, B, A, F, G, K to M. The O stars are the hottest and the bluest, and the M stars are the reddest and the coolest, in short. So that process of these hot stars that are actually doing this amazing, there we go, doing this amazing process of a supernova, they're going to be very massive, and the likelihood that they might have habitable planets is actually slim. Because it's usually these O stars that are going supernova and some B stars. And those stars we don't think can have life around them because there's too much ultraviolet radiation kicked off from the star throughout its lifetime. Number one. Number two, the star doesn't last as long. It only lasts a few millions of years, tens to 100 million years. And we know that life on Earth took 4.6 billion years. Now that was courtesy of 5 major extinction events that occurred here, slowing us down a bit. But if we didn't have any extinction events, then maybe life could have developed here in 2 billion years or 3 billion years. Don't know. So that said, if we have a star that we see that's gone supernova, most likely there wasn't a planet around it that could have housed life. But around that star system, there might be a nearby star. that we can't even hope to see with our most powerful telescopes. And that might have actually housed life. And that supernova might actually send gamma radiation and other radiation to that solar system and destroy or sterilize the planet. And so we're concerned, for instance, with what we have near us, and all the nearby stars to us are not the kind that go supernova. But that doesn't mean that's permanent, because we orbit the galaxy. We've gone around the galaxy, oh gosh, maybe 19 and a half times or so, because it takes 230 million years to go around once. And in that time, we're passing stars, they're passing us, we're crisscrossing, and they're all generally going around the galaxy all at the same time. But some stars get close to us, some stars go farther away. Right now, Alpha Centauri is the closest to us, at 4.3 light years for that triple star system. But Barnard's star is going to be close to us too. It's going to get closer than it is now to us, which I think is about 6 light years. But it won't be quite as close as Alpha Centauri is. But that said, we still have the potential that we're going to end up with a potential supernova that affects us sometime in the future. Okay, let's see what we got here.
Folks, I'm going to post a link to a NASA, I think it's a Hubble image of Messier 101. Very nice picture. And if you see the one spiral arm that's off by itself to the left, just like in Marc's image, that second bright spot down from toward the end, just to the upper left where we see the supernova, you can see that same bright spot in very high resolution, and there is no sign of the supernova, of course, because the image was taken in the past.
Yep. I want to say hi to Marianne, who's here.
Hi, Marianne.
Marianne met an astronomy great down in Sonoyta, Arizona, just a little while ago. I got to talk to him, David Levy, who was visiting an observatory down there where Marianne went to do a site search for the next SkyTour live stream telescope. David Levy, you may remember the name might sound familiar. You've heard of Comet Shoemaker Levy. David Levy, with his Newtonian telescope, was and is a comet sleuth. He hunts down comets. Very nice guy, and I finally got to talk to him tonight. It was nice. So Marianne is just down there. Yeah, she says, I just met some wonderful astronomers down here checking out areas for another telescope. Yep, that's right. Yeah. Yeah, he is. Okay. Well, we're holding our own with this scope. It's a little bit blurry because of the wind pushing our scope around out there. We have a little spider web in here. You can see the spider web is dancing about. You know. And if I move myself out of the way, you can see our third view over there, which shows you the telescope in the building. And we're looking from down, looking up through the open roof. Hey there, McKinley 5. How are you? Nice to see you. Yes, Gladys. It's blue now, and that is because it's so hot. That's why this is blue. That's the supernova right there. And just to showcase that for you again, there it is. Inside the red box, that's the supernova. Well, that's really substantially bright.
It is. And
I'm liking it.
I agree with what you said earlier. I mean, it looks like it's getting brighter as we've been looking at it tonight.
Yeah. I mean, some of that is image bloating
Yes.
as more light hits, and that's for sure. But I'm very used to image bloat, and I know what it looks like. And you'll notice that these stars, they are always about as bright as they're going to be when they first come in. This, however, has an extra rim around it of light blue, and this is light blue, and then it's actually extremely blue in the middle, and almost looks white. And that's the only star that's doing that in here, and there's a reason for that. And that's because this star, I think the flux of light is changing on us as the moments go by.
There will surely be many additional images of this coming out in the very near future.
Oh, yeah.
Some doubtless from professional observatories. We should really be getting an eyeful with this.
I think so.
And I find it interesting when you look at the whole galaxy. Forget the supernova for a second. Of the large area, the first bright area out toward the end of the same arm of the galaxy.
Yeah.
At about 9:30 or so. See that characteristic green color? And then
Right there.
yes, and if you look farther out, there's another big green one, if that's not a hot pixel, there, and another one
That's
farther
not.
to the left. But then
Yeah.
down at the lower left side, from about 6 o'clock over to 4 o'clock or so, there are
Oh, yeah, we got
several
one
more
here.
bright green areas.
Right here.
And
Yeah, these are all potential supernova remnants anyway, right?
uh-huh,
So,
that's my point.
so I think that, yeah, okay, I'm sorry. But you'll notice, look where these are occurring. These are all in the blue spiral arms. Because the blue spiral arms, they're blue for a reason. That's because most of the stars there are hot and young. The yellow in the center, these stars are the older stars. And they've been around a while. And the spiral arms in the galaxy, that's a whole world unto itself and lesson unto itself in learning about how spiral arms form, because uh, it's a very in-depth subject. Hey James, hi, how are you?
Mark, cosmic ray sort of has alluded to an interesting point. He says pitted the spectroscope is look at the inside of your bunker right now, but what would you expect to see in a spectroscope? What spectra would we see as the supernova progresses?
Well, in the supernova, you're going to see emission lines, okay? And emission lines are the lines of when you have superheated gas that is emitting light because its electrons in the atoms are driven off, and then after collisions outside in the higher levels in the atom, they come back down in, and as they lose energy and fall back into the atom to their previous levels, they actually give off light when they lose energy. And that light that they give off is what we see in the spectrum, and it's going to show up as a spike. All right, so we'll see an emission spectrum coming from a supernova. We can expect to see lines of neon and oxygen, hydrogen, and dozens of additional lines, emission lines from this. I mean, there might be, if there's other gas in the area, we might see some absorption lines of the cooler gas that's in front of the expanding supernova. But we'll see the emission spectrum of the galaxy first and foremost. I'm sorry, of the star. I'm going to pull out some of the detail here. Look at that. That is pretty. That's really nice. Okay, we're going to save this.
I mean, what would you expect to see? Hydrogen? Would you see the heavier elements later on as the supernova progresses?
Okay, well, let's think
See
about
what I'm
that.
saying?
I do. okay, we see the neutrino rush, okay? But when the star blows up, uh, it doesn't happen in stages like a planetary nebula. It's cataclysmic. It happens all at once. And it institutes something called the R process, the rapid process. Now, a lot of the elements that are created in our periodic table happen through an S process or slow process. That's called neutron capture, beta decay. In other words, a carbon atom can be converted into a nitrogen atom. All right, with the addition of some neutrons in the carbon atom, and one of those neutrons gets converted to a proton, which is, a process that occurs. And if it's converted to a proton, now the count of protons goes up by 1, meaning it goes next in the periodic table to nitrogen. Okay, if it stays that way and doesn't spontaneously decay back to something else, then we have a nitrogen atom that's been created from a carbon atom. Similarly, we can get oxygen that way as well. And a lot of other elements in the periodic table are created through that process, what we call the S process. But a supernova is not that. A supernova is rapid synthesis of heavier elements. And on SkyTour Radio, we've talked about this in depth, where we actually show that boring old periodic table, but show it in a new light, showing you where all the elements come from by looking to their sources. Okay, gold, for instance. Who knows where gold comes from? All right, gold comes from the merger of neutron stars. And when that happens, that creates some immense, explosive results. Merging black holes, merging neutron stars. These are potentially very violent events. You know? Hey, Keith Evans, how are you?
Okay, I'm going to keep
And
asking
Keith-
dumb questions. Would we or would we not see the supernova evolve, so to speak, via its spectra?
Yes. Oh, absolutely. Because remember, it's going to cool, and at a certain point, emission lines are going to end up mixing in with some absorption lines. Okay? And eventually, you won't get any more emission lines when the supernova goes away. But you will have some emission lines left in the remnant of the supernova. I mean, we see emission lines in the Veil Nebula, which is a supernova. We see emission lines in the Crab Nebula, right? But those are in our galaxy. This is in a galaxy far, far away. Okay? So we're seeing that emission, and if we could disassemble the remnant and see it in its various places, I mean, it would take a James Webb telescope caliber or more to disassemble this supernova remnant as it's forming. I mean, and we can do it. We've done it. 1987A comes to mind as one that we actually saw the echoes of the light moving through the supernova.
Right.
Just beautiful. When I say light moving through, light moves at 186,000 miles per second. Okay, roughly, it's a little more. And that's about 7 times around the Earth in a second. And when a supernova occurs tens of thousands of light years away, like, say, a companion galaxy to our own, like the Large Magellanic Cloud or something, we would see a gorgeous explosion and it would be a bright star. But then as we looked at it over coming weeks, we would see this expanding shell of light. And what is that? That's actually the speed of light, the light echo, it's called, moving through the nearby interstellar material. You know?
So, there were questions in chat earlier.
Yep.
And I guess what I was getting at when we were looking at those large O3 areas over on the lower left, they said, will the supernova turn into a nebula? And eventually it probably will, and it'll wind up looking like those green areas over at 6 o'clock and 4 o'clock.
I suspect that's true. We'll watch for it over the coming next year or so, and we'll see if there's been any change to this region. There might be, there will be a growing supernova remnant, and so that means that we're looking at something that's going to be evolving right before our eyes.
Yeah.
But at a galactic cosmic scale. So nothing happens rapidly in the universe.
Right.
Except the supernova event itself. As I said, when we know a supernova is about to occur when we get a stream of neutrinos from a certain direction. And I know that many people are looking forward, very forward, to getting a neutrino stream from Betelgeuse. You know, at 750 light years away here in our own galaxy, that would be a show to stop all shows. When Betelgeuse explodes, we're going to see that star in the daytime, in the night, in the sky. It'll be visible in the nighttime, and it'll be visible in the daytime sky. So that'll be pretty cool. So even if it doesn't happen during winter and we don't have the ability to see it, if it shows up in the daytime sky, we'll be able to photograph it. And we will. If we're there for that. Okay, I'm going to save this. This is 48 frames stacked. There we go. 16 bits. Save exactly as seen. Okay. Alright, so now what I'm going to do is I'm going to drop our gain down to 150. The higher the gain, the more grainy. And if you're wondering what that all means, these are the two most important elements here, the exposure and the gain. Okay, those two are the most important parameters in our entire setup, okay? Alright, so let's come back here. And let's do a little bit of this. You can see that. I mean, it's really bright still. It shows up very nicely. That's incredible. Okay. All right, here's what I'm going to do now. I'm going to go back to 1 second, go to our high-end view here, our what we call our night vision mode, and we see some stars. What I'm going to do now is I'm going to back out. I don't have to. This is just so you can see visually. Okay. All right, now what I'm going to do is I'm going to run my focus again. When I see my stars look like donuts, there we go. Now I focus again. Why? Because I want to get the best here, and I did not have my temperature compensation on at that point. So we're going to build a focus curve here. It's going to be a little parabolic curve. At the bottom of that curve, where the star image is the smallest and the tightest, that's our highest degree of focusing. And we will then tell the telescope to go to that point, in that focus curve, and take another picture. Michael Hedrick asking a nice intellectual question there.
Yes.
We'll get to that.
I just gave him a short, simple answer.
Would you say yes?
I said we'd have to be going really fast to be able to see any difference, see a change. I assume he's talking
All
about
right.
time dilation.
I think he was. Okay. Now we're going to come in here and going to go up to 25 seconds again. And we're going to kick ourselves out of this and go into our live stack once again. And our stars are going to be a lot more focused than what we see here. There we go. So let me just clear this. This has been saved. Away it goes. All right. Let's capture this.
Gladys has a question of you.
Okay.
Well, nice short exposure there. I swear that thing has gotten brighter.
I'm telling you. I think it has. I'm going to zoom in on this already. Look at that. That's really something. Yeah, it doesn't change much when you reduce the intensity here. What's Gladys have to say? Where is she? Hey, Chantel. Gladys says, if you could live 1 billion years more to observe the sky, would you? Of course. You know why? Because we would see the Andromeda Galaxy nearly in collision by that point with the Milky Way. It'll be much, much bigger in our sky. Not quite here yet, but it would be pretty cool. In 1 billion years from now, we will be on multiple star systems, not just this one around the sun. We only understand what it is to live around our star. But man, oh man, we will be able to journey to the stars, without a doubt. In fact, I'm leaving for California at the end of the month to talk about that, actually. What'd you say, Daryl?
To live 1 billion years, though.
Well, I would, we always talk about how fast the years pass. I think the hard part would be watching all the people you know get old and pass away. Look at that. These are much sharper focused. But I agree, that would be kind of a tough one, wouldn't it?
The first thing that came to mind when I saw that was there was a Doctor Who storyline when Matt Smith played the Doctor and Amy Pond and her husband or her boyfriend slash husband Rory were with her.
Oh, I remember
And
Rory.
yeah, and at one point Rory was a Roman soldier and
Mm-hmm.
he actually lived 2,000 years from the past to the then present day just to be with the woman he loved, Amelia Pond.
Oh,
And
yeah.
boy, imagine how 2,000 years must have dragged. I could not
I know, huh?
imagine a billion years. You're basically talking uh, close to it. Well, what am I trying to say? You know what I'm trying to say.
On a
Immor-
human scale, would feel like infinite amount of time.
Immortal.
Yeah,
Would you excuse me a minute?
sure.
Be right back.
Here we go. All right. Gladys. Hey, at least Marc will be rich by then. I don't know about that, Gladys. You don't do this to become rich. As Cosmic Ray points out, I probably would have spent it on very expensive toys by that point. I would have saved up for extremely. Well, by then, you know what? I would have my own space telescope. Let's be clear. I'd have my own space telescope. And the successors to SpaceX will have launched it. And by that point, we'll be able to do maintenance on it. Right now, Marianne and Tara run out to the observatory to do maintenance when I'm not there. And in the future, we probably would be able to do that maintenance a lot easier. Robotic, remote access to everything. Gladys says, Marc would have his own planet by then. Well, actually, good point, because remember those M-class stars I was telling you about? The M-type stars are cool, and they're small. So any planets and habitable zones around them are necessarily much closer. In fact, there's a star system called TRAPPIST-1, and there's 7 planets in TRAPPIST-1. And 3 of them might be in the habitable zone for that particular star. If you have 1, 2, and 3, I think it's like F, G, and H might be in the habitable zone. They're small letters, right? And they start with B, C, D, E, F, G, etc. I. Well, those planets might be in the habitable zone, but every one of the planets entirely in that star system are all closer to their star than Mercury is from our sun. Way closer. And that's how little energy those little stars pump out. So that's pretty cool. And that explains and tells you why having a system, having a planetary system around a star like that might be really interesting, because what's happening with those stars is they're all facing those planets going around the star are all facing the star, like our moon faces Earth. That's called tidal locking, and these tidally locked planets are gonna have some consequences. One of them is that on the facing side of the star, it's always noontime hot sun, okay? But on the edge of the planet, it's always sunset. You like taking pictures of sunsets, right? Can you imagine living on the sunset side? That's just crazy. That'd be amazing, And in those planets, you have to go all the way to the other side of the planet to see the sunrise, to see the sunrise side. But then on the far side, facing away from the sun of that star, like way over on this side over here, okay, if this star is over here toward you, on this side out here, it's perpetual night. The thing is, a year on Earth is defined by how long it takes for the Earth to go around the sun. A year on those planets, similarly, is defined by how long it takes the planet to go around its star. Every one of those planets around TRAPPIST-1 goes around the star in less than 12 days, 13 days. And the ones that are habitable, we're talking about 6 and 7 days. What does that mean? 6 and 7 Earth days it takes for a planet to go all the way around its star. Well, 365 days is a year for us. And we watch the changing sky, right? Daryl talks about how Orion and Sirius have already gone away, and now the spring constellations are up, and we're able to do stuff like this and see galaxies. Well, similarly, around a red star, where you're tidally locked, and you have a year of 6 days, you can visually watch the sky change, the season change before your eyes. Visually, you could watch the sky dance, and you'd be thinking that that's the planet rotating. Well, in a sense it is, but it's rotating only once as it goes around the star. From the top, it would go around once for every time it goes around the star. Right? But because of that tidal locking, it would be only 6 days, and you'd catch the entire view of the universe from that planet. It'd be one heck of a week, wouldn't it? You know? However, if you wanted to take pictures of M101, we'd have to have a very different set of telescopes, because we would see, and you could probably see M101 from there as well. And the thing is, that telescope would be visually moving over the course of the night as M101 continued to move across the sky at a much faster rate than our Earth is rotating out from under these objects right now. Pretty impressive. Okay, we're going to save this again. Save it exactly as seen. Okay, I'm pretty sure that we captured this very well. Let me do one thing. Let me zoom in on this again. Actually, give me a horizontal axis. I'll zoom rather. There we are. And I'm going to pull this back a little bit just to see what other detail we can see in M101. Now this is very pretty. Look at this, guys. You have this beautiful arc right here. That's an arc of hot young stars at the location where a spiral arm is just rotating out from the core. And we'll talk about how spiral arms rotate at some point, and why they all look like these spirals rather than just straight lines of stars or whatever. In short, it's called differential rotation. And if differential rotation was allowed to do its thing from the beginning of the universe, 13.8 billion years ago, when we know the first galaxies existed over just 300,000 years after the start of the universe, fully developed, thanks to James Webb, then every galaxy we see should all be wound up by now. Should all twisted around and made all big, very, very tightly wound arms. But we don't see that. And that's where a guy named Fritz Zwicky came in, Swiss astronomer, who also researched dark matter and said that there is a misunderstood matter that pervades galaxies, maybe even in a halo around the galaxy, that makes the differential rotation occur a lot slower. So they don't wind up right away. They're actually taking their time because there's other mass keeping them all in check. Very interesting theory, and the data backs it up. Hey, Judy. Judy's with us, Judy M. Cindy Murphy's here. Hi, Cindy. Nice to see you. Yeah.
Mark Chantal is asking if you're going to Pine Bush.
Oh, Chantel, I was mentioning earlier, just a few minutes ago, I won't be in Pine Bush this year. I'm going to be in California. I'm actually doing 2 talks in California at Contact in the Desert. Contact in the Desert has been a conference that focused on very different things in the past, and now it's a UFO conference. But now they're actually focusing on science a lot more, and so they asked me to speak there this year. And we're going to talk about, in layman's terms, we're going to talk about some of the advanced physics that could explain how unidentified flying objects, craft from another race or civilization, could have gotten here from either the stars or from a galaxy like this. Using some concepts in physics and string theory, but explained in lay terms so that it's very understandable. The second thing I'm doing out there is a SkyTour live stream, live with a studio audience. Instead of me just sitting all alone here in my little bunker, I'm going to be in front of thousands of people out at Contact, and I'm going to be having all of you live with me at the same time. And we're going to be doing a live SkyTour live stream event as well. Then, less than a month later, I'll be back there again, but this time not in California, but in Roswell, New Mexico, where I'm going to talk about the same thing and do another SkyTour live stream, live event. So it'll be the first time in California that we do a live event. And I'm pretty sure that it'll go off like clockwork, because all the software I need is 2,500 miles away from me. It's on the server out there. I just need my broadcast software. You know, so it's going to be kind of cool, and I have a feeling that it'll be really interesting, and I'm looking forward to it very, very much. And those are the only two events. Then I'll be filming for The Proof Is Out There in June as well. So in beginning of June is Contact in the Desert. Filming for Proof Is Out There is sort of the middle of June. At the end of June, it's out to Roswell for another conference. And then I think I'm clear at that point. Well, just in time, because I got some big aerospace and defense projects that I have to do. Many of you know I own a company called FX Models. That's a special effects models, but it's also we make prototypes of things that may not see the light of day for 25 or 30 years for the Navy, and we've got a lot of projects to do that coming up. I say a lot. There's 3, but that's going to keep me more than busy, because that'll be pretty cool. Let me see if I can coax some more data and brightness out of here while darkening the background. I have to say that Supernova has really, really just turned on. Look at that.
Yeah.
Wow. Color correct that. We have less wind right now, so I'm going to take advantage of that. Save this again. Save exactly a scene. Wow. I'm going to say this too. The telescope is performing unbelievably. Remember we looked at M101 in the past, and it just didn't look this good.
Yeah.
There's something about what's been happening. I don't understand it, but we're actually able to get a much better rendering of objects with this telescope. Even with these guiding errors you see here, look at this. There's so much wind out there that those are artifacts of the guiding. But still, we've got rock solid guiding because the telescope is managing to do that in spite of the wind right now, and that's really cool. Wow.
The really bright green object to the left of the nucleus, no, to the left.
Okay.
From the center,
This one?
farther out, the really
this
bright round right there. Is that a pixel or is that real?
No, that's real. Yeah, the pixels are going to be these long, drawn-out things from the guiding.
Yeah.
I get rid of those in final processing.
What are we looking at there?
If we,
Another O3 area? Another supernova
that's going to be.
perhaps?
I think so. If we go out to the full frame, okay, you can see what this looks like now. This is that dark area is because we started doing this before it got fully dark, and so the flat field correction that we do was sort of fooled by the extra sky brightness. We've taken a picture. Let's clear this and just do a couple others like this. We have one coming in now. Let's see what we got. Okay. That's pretty. So we did it at 150, so that's half of what we normally do for our gain, as we call it, which is the sensitivity on the chip. So that's probably going to be the best exposure of the night, because we were able to do a bright galaxy like that. Of course, our telescope that we have here is running 25 times faster than when we first bought it, because and that fast is photographically fast. Oh, I'm jealous of Marianne. I have to show you. I don't know if you'll see this, so I'll show you right now. I'm gonna show the background. Okay. This is Marianne with David Levy right now. That's the Comet Hunter Extraordinary. There he is. Isn't that cool? That's pretty cool. He is a nice guy.
I didn't see anything.
No, you didn't, because it's on the broadcast software, not on what you could see.
Oh.
Sorry about that. You'll see it in the stream if you play it back. Let me get rid of my background again. Okay. All right, so while we're here, why don't we go check out something else and give ourselves a chance to see something different than M101 today? Maybe another galaxy by chance? We have
Sounds
several.
Reasonable. Oh, yeah.
Yeah. We have several. Okay. How about the Whirlpool?
Sure.
Okay, we're going to go to the Whirlpool Galaxy right now. Actually, first things first. Let's say goodbye to this one. First, we'll get rid of the stack. We've already saved that several times. Now we'll go back to our night vision mode here. Here we are. And I'm going to take us back to 250 gain. All right. All right. And now we're going to go to the Whirlpool Galaxy. All right. And you'll see the Whirlpool come in. There it is. Whirlpool is an amazing galaxy in and of itself.
Hopefully we'll see some numbers start coming in on that supernova
Yeah,
soon.
I agree.
I'd like to see light curves or lag estimates, stuff like that.
I'd like to see spectra. Because whatever, depending on what we see in the spectrum, that'll tell us what the progenitor star was. You know, the star that caused it.
Yeah. They said it was a Type 2 supernova.
Yeah. That's a core collapse supernova.
Right.
And the core collapse supernova, guys, is what happens when you lose the ability for the star to hold itself up, and so the core collapses. And from very massive stars, what could be left behind is a neutron star, or a pulsar, or even a black hole if it's a massive enough star. All right, I think our focus is looking good, so let me do one other thing while we're here.
Don't they sometimes disintegrate and blow themselves up completely?
Yes, sometimes. Okay, we are going to do a single acquisition with our all-sky camera. 15-second shot. Oh, Michael, I'm glad you enjoyed it. Michael says, that was a real treat. Okay, there we go. All right.
Guess what the real bright thing is over in the west?
Which is over here. That's a planet, guys. And do you know which one that is?
I do.
I know you know. Let's see if anybody knows in the chat. What's the bright object over here in the west? This is north, south, east, and west. Okay, Michael Hendrick guesses Jupiter. Gladys guesses it's Venus. Anybody else? Izabela says Venus?
It is Venus.
Ta-da.
Venus was still above the horizon here at 11 o'clock last night.
Yeah, it's pretty far up there.
Which amazes me. Venus is going to be at greatest eastern elongation on June the 4th, I believe, at which time it'll be 46 degrees away from the sun.
Mm-hmm. So it'll be in the sky for hours after sunset.
Uh-huh.
Okay, we're clearing this 25-second shot of a galaxy in collision, which is the Whirlpool Galaxy. And boom. There it is. Ooh, let me correct that. We need to soften that up. There we go. There we go. That's looking pretty. Zoom in a little. Keep in mind that our field of view is 4 full moons across and 3 full moons tall. So that's 2 degrees by 1.5 degrees. Cosmic Ray says, hey, the Veil Nebula is coming up. You know how someone is drawn to that. Yes. Cosmic Ray always says, here we go into Cygnus again. Yeah, well, I think that it's very important to look at objects that are precursors to life in the universe, and that's one of them.
Yep. Cygnus is up now.
Yeah.
It's still quite low in the east-northeast, but Cygnus is up.
And the Veil will be one of the first things we can see.
Yeah. No doubt.
Mm-hmm. Okay, let's see what happened here. Okay. I just brought this up a little higher so you can see the progress bar down here. We have 5 stacked images, and you can see this beautiful, beautiful galaxy revealing itself to us. And the guiding is perfect. So I'll change the name here to Measure M51, which is what this is. It's the Whirlpool Galaxy. I don't know why I put whirlpools and then it keeps reproducing that. Alright. That's really pretty. let's put that out there. Oh, that's the wrong thing. Where the heck did that come from? That's not it. That's what it is. Eeks. Okay. There we go. Now, if you haven't subscribed to us, please do subscribe. We really enjoy your company here on an ongoing basis. Go to SkyTourLive.org or SkyTourLive.com. Both places bring you to the same thing. And check it out. On the upper left, you'll see the link to this stream. On the right is a link to our Patreon, where you can support us and join us and, you know, make sure that we can keep doing this. That'd be very helpful. You know, we have an ongoing list of patrons. We don't have that many right now. We have these guys right now. There's one more on the list. Okay. Diane H. is on there as well. So we have a lot of people that want to, and I think that it would be, I think it would be very wonderful if you could support us. Haha. C&D boy. I'm impressed with this. This is really pretty.
Can you zoom in on it yet?
I can. I think we're at the point where we can zoom in. And then I can do some operations. Yeah, lots of detail in there.
It's an interesting kind of backwards S kink in the inner spiral arm on the left side.
You mean this one here?
10 o'clock in the center. Right there.
Oh, okay.
At about 10 o'clock.
So here?
Yeah. See the big blue S?
Right here?
The inner arm to the left of center.
This is the inner arm.
The other inner arm, the one farther out.
The outer inner arm. Okay, gotcha.
Yeah.
Okay.
See the big blue S?
Yeah, this one right here, you mean?
Yeah.
Yeah. It's really cool.
The dark lanes in the orange are showing up very well tonight also.
They are. They are indeed. This is really pretty. Guiding is spot on, which I like very much.
Nice and round now.
Yeah.
Stars, that is.
Yep. Let's pop up the sharpening to the highest level so you can see how high it can get. This is just momentary stuff, but that's terrible because it makes the stars have dark halos around them. Okay. So this is pretty good. If we turn it off, you'll see that it kind of goes away. Turn it on, and you see everything is much sharper. And you'll notice, guys, that this this arm right here has a point on it. See that? And that's because this galaxy is not originally part of this galaxy. This galaxy plunged very close by, and as it went, and it's further into the page, so to speak, than this is. And so what it did was it bent the spiral arm down. That spiral arm on the outside here is actually tipping downward. So if you were to look at this from the side, right, you would see a spiral arm which goes like this. Not that little last bit. It would be bent down toward this galaxy, which is further away and down. It's really quite amazing how that happened. So it's really kind of like this. It just slopes down. And this has no relation to this. I'm just saying if you look at it from the edge, that's how it would look. It'd be sloping down like that. Very cool. Very neat. Constant Gray says, Veil syndrome, inability to not image the Veil Nebula at great length and many times. Is that a complaint, Ray? I want you go to SkyTourLive.org and select Contact Us and register your complaint. I can tell you this. Alright. Do you know why we do that, Ray? I can tell you why we do that. Because right now, we have a database with hundreds and hundreds of observations in it. Thanks to Robin Curtis, who built the database for us. And if you go to all the times we looked at the Veil, and you do a blink comparison between one and the other, you might find a change that has gone unnoticed. And so by repeatedly doing these objects, we are building a database of long-term change. You know, astronomy isn't always glitzy and glamorous. I try to make it glamorous. I mean, look at this presentation. This is really cool. You know, nice orange lighting and so forth. Weird astronomer down in the corner that's talking about things. You know, so I just think it's kind of neat. Hello, Marco. Marco's with us. That's wonderful. Alright, let's see here now. Alright, 1 second, guys. I am getting into the YouTube app on my phone. Yes, it's me. Here we go. Alright. Alright. And while we're taking some last pictures here, let me go check things out here. So we've got 28 stacked here for this so far, now 29. And that will continue to climb.
May I make a suggestion for a next object or another object?
Are you going to talk about Bode's Galaxies or a different one?
Different.
Nice. What would you like to see?
M63s.
Very good. Okay.
Should be close by.
Yeah, it's all nearby. Absolutely. Alright, 1 second here.
It's kind of hard to believe, folks, if you see a sky chart or if you actually go outside and look at the Big Dipper, it is transiting the meridian already, the line that passes straight overhead. north-south.
Yep.
It's like hitting its peak already, and it's not even summertime yet.
That's right. Then again, it's also um, almost 1 a.m. here.
Well,
Okay.
in Connecticut, but yeah, not in Arizona.
No, it's 10 o'clock out there.
Yeah.
So it's we've done 32 here. So we can clear this now. This is available online. That's the nice thing about us. All of our photos are available. You go to skytourlive.org and scroll down, and you'll see "Take Me to Cool Pictures," and it'll take you to the directories and show you how to get a hold of all these pictures for yourself. 1 second of time, and then get rid of this stack here. That's cool. All right. And there's our image. Okay. So, M63, huh?
Please.
All right. Let me just do this. All right. Let's go over here now.
I did send it to you yesterday, but yesterday's APOD photo was M63.
All right.
A very deep exposure.
The Sunflower Galaxy.
Right.
All right. We've done that.
Really cool picture.
All right. Well, we're going to check it out. Here we go. See the telescope moving right here. Didn't move too far because it's right nearby. And there it is, right there. We're actually a little zoomed in right now. So we can move that like that. Let's see. Let's pull this. Yeah, that's what I thought. We're a little bit off a little bit. That's fine. Okay, so we're going to just go south a little bit. There we are. And then we'll go west a little bit. That's good. All right. One more zap. Okay. And now we'll let it capture. If we go into our status here, you'll see that the telescope is searching for a guide star. That's what you see up top there. And it's already found them. And once it stabilizes, we're going to go in here and take care of this right now. At 250 gain, that's good. So what we're going to do now is we're going to do a 25-second exposure. We don't have to go much more than that for these galaxies are so bright. You know? And so we're going to get rid of that. And we're going to go into our live stack and remove our previous shot. And then right away we're going to get our new shot. There we go. Sunflower. Alright, we're going to let this come in a little bit, and you'll see we have 2 in here already that are captured, and it's already starting to look really pretty. We can start to see some real nice details in here. Very happy with that. Looking pretty. Gladys, welcome to the Magic School Bus. That's Miss Frizzle, for those that don't know. Because she says, Marc is our Miss Frizzle. I own a tux, you know. She says I should wear a tux. I own a tux, and to take you on a formal tour of the universe, I might have to wear it. Well, I'll be wearing a sport coat and tie when I do this out in California, I think. Depends on the temperature. It's probably going to be 90 because I'm doing this outside. There's thousands of people at this event, and it's a huge event. So I'm probably going to have to dress to the occasion. So I'm not sure how long, or how that'll work, but I can do that. I usually wear a suit and tie. I mean, because I figure, you know, if you're coming to see me talk, I'm not going to show up in a t-shirt and jeans. Because I'm supposed to show you the same respect. I want to show you the same respect that you're showing me by showing up. So...
Are you eating something?
Tums.
Ah.
I just had 2 Tums. Sorry about that.
I was going to say, I hope you brought enough for everybody, but never mind if it's Tums.
Actually, Tums is a great source of calcium. Look at this. Sunflower never ceases to amaze. Look at all the detail in there. We're at 9, going on 10 exposures. Look at that.
Oh, the APOD for yesterday was an extremely deep exposure. I should have sent it to you.
It's all right. I'm turning off the unsharp mask on this because I like to show some of the detail in the center. And the unsharp mask, which is a way of sharpening and making more detail, can also overexpose the nucleus a little bit, like that. And in this particular galaxy, that doesn't really help too much. So I'll leave it off for this galaxy, and I'm just going to drop this down just a tiny bit. There we go. Look at that. Really pretty. That's the Sunflower Galaxy.
Dark bar across the lower left portion of the galaxy.
Mm-hmm. Yep.
And another one closer to the lower right.
We got this one. Right there.
Yes.
And then we have this curving one you can see very clearly right there. That's the same part of the same one.
You see the real dark one to the lower left right there?
Right there, yeah. Let's see if there's more out there to be seen. And we're gonna pull back the covers a little bit and start to do what's called push processing. Like that. And then take this and move it in. Let's see what that shows us in a bit. Look at that. There's stuff out here. See that?
Oh, yeah.
And there's stuff here.
You're barely scratching the surface.
Oh, I'm sure. I'm only doing a 25-second shot.
Yeah.
You know, with the way with the setup I have here, I can do minutes of shots, but I don't want to make people sit through waiting for one single image to come in over many minutes and then do that 30 times. That's what you do when you're working. That's what you do when you're working alone.
Yep. Just saying.
Yep. Hey, Prow, how you doing? Good to see you. Michael, you said, did we say when this is? When what is? Thank you, Izabela, for putting the link up there. Hey, Genghis. Izabela, if there's an artifact on there, on the Whirlpool image, as you suggested, it's probably due to the wind. So I'll have to check it out. If you look here, where you see these red and blue, these are the pixels that, on this particular image, are dead pixels. Alright, and you'll notice, in this particular case, they're not streaked. So we're not getting any wind at all on this image. This is a round dot. This is a round dot.
I'm going to send you a link to the image she's talking about, Mark. It looks like the Eye of Sauron, except it's green down to the lower left of the galaxy.
Okay.
It's really bizarre looking.
You're talking about the M63s. It's a link I see now?
No, the M51, the Whirlpool link.
Oh, okay. Oh, I see you're doing something now. You sent me a OneDrive. I'm not sure that worked or not. You sent me a OneDrive link.
Yeah, sorry.
That's all right. So,
let me grab her link.
Okay. Who's her?
Izabela's link.
Oh, okay. Wow. This is looking really pretty.
Oh, it's going to do it again.
Yeah.
If you see her link in chat, if you can click on that, it'll show up for you. It won't seem to post for me.
Okay.
In our chat.
This is really something.
Looks like a great big green and blue Eye of Sauron.
You're back in the Whirlpool again.
Yeah.
Okay.
Referring to that image she talked about. Strange artifact in the Whirlpool Galaxy image.
Cosmic Ray. SkyTour livestream is a community, Ray, and you know, if people come into the chat, it's a social event for everybody, and I don't expect them to only talk about astronomy, and I won't enforce that actually. There are streams that will just talk about astronomy and boot you if you don't. I won't do that. people are here to enjoy what we do. For the most part, they're very much enjoying it. I've never had a single complaint about what we do, except from you. You're the only one that complains. And I don't know if it's a complaint, but this is my stream, and I have rules, and no foul language, that kind of thing. But if people want to talk about other things in my chat, that's fine. We're all friends. It's the SkyTour family, So, try not to be that one guy who stands out for all the wrong reasons. Because you have a lot to offer, and you're a smart guy. So, share with us rather than complain about us. All right, we're up to 28 shots here. We'll go to 30 on the Sunflower Galaxy. We've been playing around in the northern sky all night. I think that's pretty cool. Hey, Fantasy, how you doing, man? That's right, we've known each other for a long time. Oh, snap indeed. Hey, I'm the guy that overloads us with astronomy talk, and that's okay. Yeah, that's cool, Fantasy. I'm glad you are hanging out and lurking with us. Lurking is good. Yeah, when Scorpius is up, it's up now actually, but I don't know if it's up above our wall. The next telescope will be able to see Scorpius much easier because I've designed the new enclosure. It's not going to be a building like this one. It's going to be an enclosure which just encloses the telescope, and when it opens, it's going to open on a pier, and the sides are going to drop down below. So the telescope will be fully exposed to the horizons. We'll be able to look at trees and sand out in the desert if we wanted to. The only problem with that is that wind will then have a more pronounced effect. But I will have the ability to move the sides up and to help shield a little bit as we go. So I could literally, if we're looking in that direction, I could bring one side all the way up, kind of a thing. Because the idea is that no matter what direction the telescope's in or where it's pointing, you could close the building without having to worry about the telescope being out of the way. So that'll be cool. By the way, for those just joining us, this is the view of our new camera view, one of the new camera views. We actually get to see up past the object in the sky, of the telescope, and we can see the sky beyond. We can't see the stars because we're using an infrared illuminator to light up the telescope, but effectively think of it as you're sitting on the floor looking up at the telescope. Kind of neat. Kind of neat. All right. We'll bring that back down. Where was that? Well, that's actually right here, sitting behind me. Okay, we're at 36 on the sunflower. I think we're done. That looks really pretty.
Can you zoom down there a little before we leave?
Yeah. I'm going to save it first. Okay, 16-bit stack has been saved. Save exactly as seen. Excellent. Now let's zoom in. Look at that. A lot of nice detail in there.
Uh-huh. The big dark bar at lower left really stands out now.
This one here, yeah. Interesting, huh? You can see much more is out here. Let's see if color correction does anything for us. Slightly. And we kick down the red a notch. And let's lighten up the background just enough to be able to then push some detail. Okay, and now let's take this and bring that dark peak back. Okay. What I did necessarily does make it look a little, more fuzzy. But I'm trying to show where we are with this. This is pretty cool. This is a good setting. Yeah. You can see that right there. That's really nice. There's a lot of detail in there. Okay. Okay. Well, there we go. That's really cool. We'll clear this. We've done this now. 40 some odd exposures. We'll clear it. Go back to our night vision mode so we can see exactly what is going on. And there it is. There is the galaxy. Turned out to be a remarkably clear night out there. It wasn't. It was supposed to be cloudy, but it got better. It got better. Now I want to take us to. I want to take us to a beautiful star. This is the middle star in the handle of the Big Dipper. It's called Mizar.
And Alcor.
And Alcor, there they are. Very, very bright. Yep, there they are.
It was supposedly an old naked eye test of visual acuity.
That's right. I used to be able to see it. I may still be able to in Arizona. Okay. I'm going to pull these up a little more.
I used to have eyes like a hawk. I have eyes like a half-blind hawk now. I don't easily see Alcor anymore. Naked eye.
Yeah. I haven't tried recently, so I may not be able to see it either. Of course, I was profoundly blind only 7.5 years ago, right? So I need to try and test my vision again, see if I got anything, how much of it's really gone. Okay. So there we go. This is Mizar and Alcor. Let's do a 15-second shot of this. And we'll stack it. We're underway. We're actually going on our guiding up there. And we'll get this out of the way. This is a curve, and this is a curve, and you can adjust both. This one allows us to see detail hiding in the background, but only after. Okay, there's Mizar and Alcor. You'll notice that the halos are really bluish. That's because Mizar and Alcor are extremely bright, and those halos are due to the optics in our telescope.
If you look at the Big Dipper, Mizar and Alcor are the middle star in the handle, where the crook in the handle is. If you ever look at them naked eye, see if you Mizar is the bright one, and if you look closely, right next to it is a slightly dimmer one, and that's Alcor. And if you can see them both naked eye, well, you have pretty good eyesight.
Yep. C&D boy, I in fact do have Clem and the tractor saved. Hello, Susan Woodcarver, and hello, James Dugan. James Dugan from Down Under in Australia joining us tonight. Great to see you. I just wanted to do these real quick. I'm going to use these as a test of a halo reduction technique that we're using now. So I'm going to name these Mizar and Alcor. Alright. And we'll save them. We don't need many. It's just a test shot. Okay. Save exactly a scene. Alright. Alright, now we can get rid of it. And go back to our 1 second shot. Well, that's what they look like. Alright. Now, while we're in this general vicinity, actually let's go all the way around. Let's see if we can. I gotta check this out. See if we can see it. Oh, we can. There we go. I'm going to show you Measure 13, one of Daryl's favorite clusters.
I used to be able to see this naked eye.
I could too.
Dark sky.
Yeah. See the telescope moving over there. You'll see the cluster show up. It'll be pretty obvious. There it is. All right. Globular clusters are what are called halo objects. And no, they don't play Halo, but they actually do. Exist outside the galactic main body, and they'll orbit around the galaxy. And some of them will pass through the disk of the galaxy and out the other side, and plunge in and out as they go around, shedding stars, gaining stars. But it's a famous cluster. And before actually zooming or taking any kind of a photo, I would like to zoom in on it just to show you a feature. We'll let this stabilize here. You can start to see it, Daryl. It's right there.
Oh, yeah.
This is called, as Daryl has told you many times, the propeller. It's like a 3-bladed propeller. It's just an asterism. It's just a pattern in the stars. If you look hard enough, you can see a pattern of stars in almost anything you look at. But if you really want to see how this looks, then you do something like a 15-second exposure like I'm doing now. And I'm going to drop the gain down to 200 here. So we'll have less noise. It'll be really kind of cool. So it's going. And we'll go into the live stack here. And clear this. Last one. And boom. There you go, guys. Look at that. That's really pretty.
Yep.
The propeller is really obvious right there.
M13 is the biggest and brightest globular visible in the northern sky.
Well, Omega Centauri can be seen at this location, which is, 3 times bigger than this?
Yeah, it's in the southern sky, strictly speaking.
I guess so, right, when you consider below the equator, but we can see it. It's only 6 degrees above our horizon down there, but with the next telescope, we'll be able to see it directly.
Oh, yeah.
Isn't that beautiful, guys? That's pretty. In fact, let's just do one thing. I'm gonna take this out of the way and move my telescope out of the way for a minute and bring us to full screen here, and then move this over. Look at that. That's just so pretty. Hard to believe these things actually exist, right? You know? Let's one thing I want to do is just quickly come in here, and I want to just change some of the settings a little bit. Let's start to dig into the core. See, by moving this slider, we can start looking into the core of this cluster. And see, it's all resolved all the way into the center of that cluster. You can see all the little stars in there. Yeah. And then if we bring it back, we go too far, and we can literally overexpose it. Check it out. So now it's overexposed. But look at, those are all tens of thousands of stars in this cluster. The best place to be, though, with this cluster is right about, I'd say, pull this down just a little bit, keep it off of the overexposed, just about here. Maybe right around there. That's pretty, isn't it?
It is.
Yeah, and let's zoom in. I'm going to head into the cluster. Ah! Now you can see the pixelated stars themselves.
They estimate M13 here has somewhere between 300,000 and 500,000 stars in it. If you ever get to see Omega Centauri, it has, I think if I remember correctly, over 4 million stars in it. So much bigger than M13 is.
Yeah. Now I'm going to add the unsharp mask to sharpen it. And now you see what it does. There we go. That's pretty cool.
These are some of the oldest objects in the universe, too.
That's right. I was not gonna get into that, but now that you mentioned it, I think it probably is a good idea. Basically, what we're looking at here with this mesh of 13, pull it down, is these stars were formed around the beginning of the universe. Now, our sun will live about 10 billion years, and the stars in here were formed just shortly after the beginning of the universe. So, when the first galaxy was fully formed, turns out was around 300,000 years after the beginning of the universe, which has been giving cosmologists a bit of a problem, because no one thought that a fully formed galaxy could exist that early after the universe. After the universe started. So it appears that maybe a couple things might be wrong with our thought processes. It could be that the universe is older than we thought, or it could be that we have misunderstood galaxy formation, and more. So there's a lot of things. There's a lot of things here. Now, the other thing about these stars is, you might say, wow, a big cluster like that, can you imagine being on a planet around the star in there? Unfortunately, there may not be very many planets around stars and globular clusters, unless they get picked up from the galactic disk, with a star that's capable. And the reason is because these stars formed when mostly hydrogen and helium was in the universe. And they are only making carbon, nitrogen, oxygen maybe. And very few of them have gone into planetary nebula stage, where they have died and become like the helix, or the ring nebula, or the dumbbell nebula, or the blue blinking planetary. So it's only then when they're going to expel their elements into the universe, and not a great many have done that yet. So most of the stars in the globular clusters are still there from the very beginning of when they were formed. So the likelihood that there's a rich playground for planets to form in there is very low. It doesn't mean that they don't have them. They do. There are some that are possibly in these clusters, but none so far that we can see. Ray, you mentioned the Eastern Observatory. No, there's going to be an Eastern Observatory. It's going to be the same clamshell design building that I've designed for the second Arizona scope. And Marianne is down in Sonoyta, Arizona right now, looking at that other site where it might be advantageous for us to put another observatory. So we're thinking about it. And that'd be for another telescope down the line. Okay, so this is a good rendering. I hope you guys like this. Isn't this pretty? It is.
It is?
Yes, it is.
I never understood why some telescopes show the propeller quite plainly and some don't show it at all.
I think that's it. All comes down to just the capability of the optics. You know, can it resolve enough of the cluster that you'd be able to actually see this or not? You know, hard to know. You know,
Some
it's
say
hard to know.
globular clusters are the remnants of old galaxy nuclei that got absorbed into their host galaxies.
Well, I can understand that, and you're right. I've seen that. But let me move this up. But the reason that I don't think that's true is because of the symmetry that we see with galaxies. It's not just the Milky Way. Andromeda has a lot of globular clusters. Messier 33 in Triangulum has a lot of globular clusters. Other galaxies have lots of globular clusters. And so we're not the only ones. So that symmetry of these halo objects seems odd. We'd expect to see perhaps some wildly elliptical orbits for these old cores of galaxies, but we really don't. So I think that maybe it's an inherent cluster that's formed at the early stages, potentially, of a galaxy's formation. But how does it form, and why, with such regularity, do we see globular clusters around galaxies like this? I don't know. I don't know the theories because no one knows the theories. No one knows why. You know?
Izabela touched on something a little bit
I'm going
ago.
to save
Let me
this.
go back and find it.
Okay.
They're talking about so-called Type 3 stars now.
Yeah. Population 3?
Yeah, population 3, whatever. And I think it's the same thing. There's some talk about it's more Webb telescope discovery stuff, I guess.
Yeah.
Some of the oldest stars in the universe, they were so big that we can't imagine. They said they might mass like 10,000 suns mass in a single star. Sounds crazy, but
Yeah. Hey, Sam S.
makes you wonder if that might be the missing mass or the dark matter, whatever.
Yeah.
Anyway, globular clusters sure are pretty.
They are. Cosmic ray is correct. You know, this looks beautiful in a good refractor. Without a doubt. Cosmic ray, I just have to correct one thing you said there. You said that this is one of my hobbies, along with my many jobs. Not much time to set up observatory. Actually, COVID dictated whether the Eastern Observatory was going to get built. There was not a single 2x4 that you could get for less than $6 when they used to be like $1.50. All right. And that skyrocketed the price of building the building here. And I'm glad I didn't do it. Now that I've got a new design, it's just going to be an enclosure. And same thing for Arizona. I would have done the one that currently is as an enclosure had I thought about it, had I realized that it was going to house one telescope. But it's pretty cool. I'm really pleased with how it turned out. And it took about a straight year, just to figure out all the intricacies of communication. Because don't forget, this has to work from over 2,000 miles away. I can't go out there into the yard and fix it if it goes bad. I have to have backup plans. I have to have a way around problems, and there's still problems that punch through all those careful things we've done. And so it's taken some time to get this right, and even so, it can still fail sometimes. I've had frightening moments when I could not close the building because something failed, and we ended up having a problem where it would close and open again. No, we had to have people come out and fix that. Hey, Dean Bustador, good to see you. So we've had our share of problems, but the more we do it, it's getting better. Here's another thing to consider. Think about the fact. Let me bring my telescope back. Okay, right now anyway. Okay, think about this. I'm risking tens of thousands of dollars of equipment out there, actually. You don't see other equipment that's behind the scenes. Okay? But I'm risking that every day I open that dome of that building. I'm risking that equipment. So I have to be reasonably assured that it's not going to go very, very bad. And if you think about it, what's our track record been? It's been pretty good, hasn't it? Except for an occasional failure where we couldn't stream. We've done okay. And I'm really pleased. Now, I have to say that people that helped with the GoFundMe initially, and now with the Patreon, that makes a lot of difference, because that means I can actually afford to design a proper building for the next telescope and go on and on. Because it's not a hobby, okay? I'm a professional astronomer. And so I think, if anything, the other jobs I have are hobbies. This is what I really do for a living, what you see here. Okay. So, and he's asking now, is the horizon in Connecticut that great for a clamshell? No, what it's good for is to set up a building that actually operates with this system and to see the functionality. I have these two linear actuators, and depending on how you hook them up, they can push out these shells and bring in the shells, or do a little bit of each one. Okay, and like I said, no matter which way the telescope is pointing inside there, these can both close. That's the idea. So it doesn't matter. So if I want to block wind, I can move one up a little bit to block wind coming from that side or from this side. And, you know, that's something that will be helpful. You know, having complete control is really cool. All right. We're going to save it one more time here. We have got a lot. We'll get 63 images here of Measure 13. There we are. And we'll save it one more time. Okay. And now we can get out of it. And go back. There we are. Nice. Okay. Now we'll zoom out to our full frame view, nearly full frame view. Okay. Let's take another look at our all sky cam. Do an acquisition. We'll go to full screen with that. Okay. There's the full screen preview. You'll see the stars visibly move here in just a sec. That's a good one. Look at that, guys. Look at that. Isn't that funny?
Giant bug from outer space.
Now we got the bug from outer space on there. That's funny. That's a keeper. That's a keeper. I think that's hilarious.
Science fiction story years ago. Don't remember who wrote it. Some giant insect came from outer space and landed on Earth, and it was like a grasshopper on an apple. It was so big.
Oh wow! So with every step, it's wiping stuff out.
I guess. Well, I remember it just sat there for a long time, a very long time, but it like freaked society out so bad, you know.
Giant bug from outer space. Yeah, I can see it. I could see it doing that. All right, that's great. All right. Let's head down here. Notice that Vega is up here. And I start to see, oh look, Cygnus, just like we know. And guess what that means, Ray? The Veil Nebula. Yes, sir.
It's not high enough yet, is it?
I don't think so. Oh, is that on the other side? I never remember. Yeah, it is. It's down way too low. Okay. But it'd be kind of funny to see if we could see anything. Let's see if we can go to Vega. Well, actually, I'll know if we can. I'll just do the check here. 35? Oh, we might see Vega. Let's check it out. There we go. Yeah, look at where the telescope's leaning way over. Well, there it is. We got it. Here comes summer, guys. Summer is approaching. And this telescope shows us where we're looking. We're leaning way over into the northeast right now. Okay. Okay.
Vega is the brightest star in the sky.
Yes, it is.
Arcturus is the fourth brightest. You
You
can
mean
see
in the
them
summer
both.
sky, you mean?
I'm sorry,
The summer sky, you mean, because Sirius is the brightest.
I said fourth brightest.
Oh, I thought you said the brightest.
No, fourth brightest.
Oh, okay.
Uh, Arcturus, Vega is fifth, Arcturus is fourth. You can see them both this time of year.
Mm-hmm.
If you look at them, you might think Vega is brighter, but that's just because it's bluer.
Mm-hmm.
Arcturus is actually just a hair brighter than Vega is.
Okay.
Is that the double?
You got it. Okay, so we need to refocus for. Well, we're kind of crippled because we're looking through some wood at the end here. So
Yeah.
let me try to see if we can fudge
That's
it.
the double in Lyra, folks. That's up
That's
at the
right.
top of Lyra with, along with Vega, the little triangle at one end. It's like a triangle
Mm-hmm.
on top of a parallelogram. The double, each of those two stars is a double by itself. Marc probably doesn't have the focal length to be able to split them, though.
Challenge accepted.
Okay.
Okay. All right. I know that my guide scope can't guide at this point, but that's okay. I'm going to move east a little bit. Okay. Okay, now we're going to do this. We're going to bring down our exposure. Actually, first things first, I'm going to bring the gain all the way down to 0. So gain is 0. And now I'm going to reduce our exposure to 125 milliseconds. Okay, we're going to keep going down. And it's low on the horizon, plus we're seeing it through a mess, but every now and then you can see the split occurring. You can see them splitting. Can you see that? Of course, every second it's rising higher too. If I turn off the tracking, all right, it won't track, and now you'll watch the stars are going to drift. Okay, there they go. And the telescope's on its side, so they're actually drifting toward the west by that much every second. So then, let's do this. We go back to tracking. All right, and you can start to see that they're splitting, but it's kind of tough. We can do this, and then increase the exposure until we can just barely see them. Okay. Hello.
What happened?
I lost the connection, and It was a glitch on the computer at this end, though. But let me just bring it back. All right.
See.
There we are.
Excuse me a second, please.
All right. Well, once it gets higher in the sky, I know I can split it because I have. I have split this. Okay. Well, that said, oh, I didn't need this. Sorry. So, let's drop down to this guy again. And let's increase our gain from 0 back to 200. And set us up to 1 second again for our night vision mode. All right. Okay. Okay, so that said, we now know our limits. So what I'm going to do is stick to things that are more west. We'll get to Cygnus, and we'll get to that wonderful Veil Nebula. That'll happen soon. Yeah, where is that guy? I think that's in our southeast sky. So here's Antares right here, and that is the Scorpion right there, that you can see. All right, the Scorpion, there's the claws. And so right now it's 20 to 30 degrees above the horizon. Here comes the summer sky. That's going to be just beautiful. But we do have Virgo, which is really high in the sky right now. And so I think what we might want to look at is some of the Virgo galaxies, which are really cool. And first one, we're just going to use this to get us in the neighborhood, because this is something that's interesting. Because here, when you come into this area, look at all the galaxies that show up. Isn't this amazing? And what I want to do is actually take us here, okay, to the eyes. The eyes have it. And you'll watch the telescope moving around here. You watch it here.
Hello?
It's going to swing. Yeah, I'm here.
Share the screen.
What happened? Why did the screen go away?
It went away when whatever happened.
Interesting. Alright. Alright, so let's do this again then. Okay. Oops, wrong screen. One second, guys. First of all, we have our galaxies here. And let me just take care of this. Okay. Now move it down. And it's just astonishing to see how many galaxies are in one view. Okay. And I'll go to 250 for this. We'll let it stabilize here, and then we're going to go to a 30-second shot. Okay, takes about 14 seconds to get our guide star. There we go. And we're underway. And now we'll do our shot. Come out of night vision mode, go into stack mode, get rid of the previous image. And this globular cluster is up on the server. Okay. This is good music for this particular location in the night sky. Look at that. It's galaxy heaven out there.
Oh. Markarian's chain, I do believe.
And the eyes.
I see a face there at the lower right.
Yeah, right? This little mouth here and a nose and two eyes and a tiny little Charlie Chaplin hat. Right?
Uh-huh.
And we'll move this down a little bit to get rid of some of the noise.
It's almost midnight here. I'm going to turn into a pumpkin pretty soon.
It's 2 a.m. here. I haven't streamed in weeks.
Yeah.
I'll make this the last object. Or objects. So how many galaxies can you count, guys? Let's zoom out a little bit. Because this down here, this is the galaxy in which we found the very, very large black hole that's 5 to 6 times the size of our solar system.
Yeah.
In the center of this galaxy, this is Messier 87. And zooming in on Messier 87, I think I have too much exposure, not enough stacked yet. We could see the jet that comes out of Messier 87 at about 2 o'clock. Look at that. So again, when you go to SkyTourLive.org or SkyTourLive.com, we have both, and you go to the Take Me to Cool Pictures, this one I'm gonna name for you, and you'll see it right here. Okay, the name is going to be the Virgo cluster and of galaxies. All right, and it's not all of them, but it's some of them.
Yeah.
And when you look at this, just want you to count all the galaxies, and you notice like there's, well, we could talk about them. Okay, here's a galaxy, here's a galaxy. Okay, here's a galaxy, here's a galaxy, here's a galaxy, there's a galaxy. See, I'm giving you help on your homework. Obviously, that's a galaxy.
This is just
Again,
a
this
tiny
is
part of all the galaxies in the Virgo cluster.
Yeah, and that's Messier 87. Yeah, and again, you see there's a galaxy here, there's a galaxy here. Okay, there's 2 there. And it's just the beginning. There's a little tiny galaxy here. There's a galaxy right here. And think about this, okay? We have all these galaxies here, all these galaxies, and it just keeps going. There's many more. Okay, some of these are closer, some of these are farther away, some of these are massive. I still haven't outlined all the galaxies that are visible here. There's way more. I mean, This one here. This one here. And there's more. But here's what you think about. When you look at these galaxies, look, there's one right here. There's one right here. And you think about this. Somewhere in here, we might be looking at civilizations. Many civilizations. It might be just, really in the prime of their existence. And this is not all of them. This is just some of them. Okay? So we're looking at a universe that I think is populated. And that's why I call it a populated universe. And that is the name of my book, The Populated Universe, and it talks about the prevalence of life in the universe based on the materials to make life that we see everywhere we look. So I think that's pretty interesting, and I'll just wipe that away for now. Everywhere we look, we see potential for life elsewhere. Now, one thing I don't know is why this galaxy is so blue. Oh, thank you, Starlink. It's true. I don't know why it's blue, but it is. Let's darken this up.
When we look at M87 there in the lower left-hand corner,
Yeah.
God, I forget it. There's like at least 1 trillion stars in that one galaxy alone.
Oh yeah, that's a big one.
That's the heart of the cluster, folks. All the we're being pulled toward the Virgo cluster, and M87 there is the central mass in the whole cluster.
Yeah.
Everything else is clustered around it.
Yeah. And MLR, he mentions the vastness of time is the biggest potential segregator. Yeah, and if you had to worry about traveling point to point in the universe, exactly. But truth is stranger than fiction. In fact, truth is stranger than science fiction. Whereas the Starship Enterprise had warp drive. Scotty, we've got to go now. Aye, sir. I'll get you going as fast as I can, but I'd have to get some sodium brandy. But the thing is, going point to point in the universe is senseless. It doesn't make any sense, because that means going from one corner to the other, going from star to star or galaxy to galaxy. But what if you could fold space and bring those points right near each other and only traverse the tiny distance between them and then unfold space? Now you're here, and you didn't go anywhere near here. You didn't go through here. That concept is called the Alcubierre drive, and that is something that is possible, but you need vast amounts of energy to do it. Okay, well, we're trying to solve that problem. However, what if you wanted to go even farther away, faster, easier, quicker? There's another way, and that has to do with string theory and a concept within a particular variation of string theory. That variation is called Randall-Sundrum 1, RS1. And what's it mean? It means that we look at the fact that we live on an X, Y, and Z universe that's moving through time. Okay? But right next to our universe is another universe, kind of like capacitor plates, right, near each other. And this here is called the bulk, BULK, and it's highly warped. So that if we can leave this dimensional space, these 4 dimensions, and go into this dimension, which is the 5th dimension, okay, then by going into the 5th dimension, the farther we go, the more warped it is. And when it's warped, it brings all the distances down to small quantities. So the farther in you go, the closer everything else is to you. And this isn't just some fantasy. This is actually worked out from the physics of string theory and looking at how this concept works. So if you could generate particles that would take your ship into that fifth dimension, then you could go in there and then basically effectively punch out of the 4 dimensions you're in now, X, Y, and Z moving through time, and go into this fifth dimension and then punch back in to the four dimensions again, almost anywhere else. And so you have an exit point and an entry point back, exit point from the universe and entry point to our universe. And that concept, right, is something that my friend Bob Schroeder came up with, aerospace engineer, and there's a number of physicists and astrophysicists who are on board with it and think this is the way it works. Michio Kaku might even be on board with this. I haven't talked to him, but I actually plan on doing so. And so the point being that if this works, then it gives us a way to make the universe a small place. All right, smaller than it currently is. So you could go intergalactic. You could go across the solar system in seconds. You could go from star to star in minutes. And you could go from galaxy to galaxy in months using this possibility. And that's, I talk about that in layman's terms because it relates to the fundamental forces that we have. We have the strong force, the strong nuclear force. We have the weak nuclear force. We have electromagnetic, light, and we have gravity. So how those interact with each other dictates the leverage we have to bring to bear with the universe to try and actually get ourselves out there. And I think this is something that is the way it's going to be. And I think that's how alien life in the universe has gotten here from there. So I'll leave you with that for tonight. I do wish to thank you for coming out tonight. This is our last object for tonight. I will save it for us. I'll do that right now. Complete with the free trail from the Starlink satellite that came through. So I do want to thank you for coming here and hanging with me tonight. This is the first time in a few weeks that we've gotten to do this. And I have a feeling that we will be back again pretty soon because it's going to be clear for at least the next week and into the foreseeable future. So thank you. Great to see you. I hope to see you again. For those that are just joining us, please subscribe, hit the sub button, subscribe, click the bell, and select all notifications so you know when we go live. Because when we see that we're going live, I keep doing my thing, and I'll run the show for a little while before saying anything of substance to allow you all to come in. So thanks, guys. You have a good night, and we'll see you again on the next clear night.
Good night, everybody.
Keep looking up, folks. Good night.